हेलो। हेलो। Hello, 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 hello.
Hello. Yes, sir.
Yeah.
Yeah, please
So
proceed, sir.
yes. So I think we can start now the lecture. Okay. Am I audible to all of you?
मतलब sir.
Yeah. So let me share the slides. Okay. I'll share the slide first. Okay. So good evening, all of you. Yeah. So good evening, all of you. Since yesterday we have started the part which is related to the testing of polymers or polymeric materials, or you can say plastics. Okay. So in that we had seen in yesterday's lecture the major part of testing of polymer is nothing but the identification of polymeric material through different processes, or you can say through different type of testings. Starts from basics like flotation method to the hot rod penetration method to the like incineration in that way. Okay. So we have seen even the chemical identification of your plastics. Okay. So in that way we have seen different methods to identify the plastic materials. Okay. So even we have started the mechanical properties in yesterday's lecture, the testing which are being used to test your polymeric against the mechanical properties, or to study the mechanical properties of your polymeric material. Correct. In that also we have started with the flexural test. Correct. In that we have seen two type of flexural test over there. One is nothing but your 3 point bending, and second is your 3 point bending and 4 point bending. Okay. In that also we have studied what kind of specimen is required to test, what why that test is important, and what all kind of results we are getting out of means by doing that test. Okay. And which kind of polymeric properties we can study using that specific test. Okay. So in today's lecture we will move forward with the tensile test method. Okay. All of you can able to see the slides? Yes. Hello. Hello.
Yes, we can see.
Yeah.
And today, what we are going to cover?
Yeah. Today, as we have started yesterday, the part of testing, it is nothing but the mechanical test. Okay. In that we have already covered up the part of flexural test in yesterday's lecture. Okay. So today we will start with like tensile test. Okay. So what all kind of parameters, or what all kind of test we can perform, or what all kind of properties we can understand using this kind of test, we will see in today's lecture. Okay. So what do you mean by tensile? Okay. So tensile is nothing but the property of a material by which we can understand its mechanical strength. Okay. Whatever the forces applied on your material, or whatever the different kind of force action will take place on your material, that part we can study using this kind of test. Okay. So in that also what all kind of parameters we can study using tensile test for polymeric materials are nothing but the stress, strain, means water stress, the deformation of your polymeric material by applying some specific amount or some specific stress on it, or we can say force on it. Okay, then its behavior against that applied stress, which is nothing but in that also we can study like elastic behavior, plastic behavior, or all kind of properties like toughness of polymeric material, ductility, or any kind of like brittle or hardness in that way. Okay, so all these kind of properties of polymeric material we can study using the mechanical test, which is nothing but the tensile test. Okay, so one by one we will see, or one by one we will study the part using in next slide. Okay, so these are, in this slide we have provided some standards which generally used to analyze, or we generally use to test the polymeric material. Okay, using tensile testing. Okay, first of all, which is nothing but the plastic tensile strength. Okay, which is having the specific standard of ASTM, which is nothing but a D638. Okay, as one of you have mentioned, like which all kind of standards we can use to analyze the mechanical properties. So in this slide we have mentioned all of the tensile properties and its related ASTM standards. Okay, hello, yes. So out of that, we will out of this all kind of tensile test, we will start with we will one by one we will see the different test procedures and different tests for the polymeric materials. First of all, we will see the stress strain testing, which is nothing but the to generate the yield of, or you can say tensile strength of the polymeric material. What all things are there in this test? Generally, if you see the diagrams over here, we generally use the specimen with dumbbell type of shape. If you can able to see the picture over here, can you able to see this cursor? Yes, hello, 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 hello.
Yes, sir.
Yeah, I think no one is responding. Okay, so I think I'm audible to all of you, but only the thing is no one is responding. That's why uh, I'm just checking. Hello,
तुमचा आवाज फार कमी येतोय सर.
hello.
हा, इट
Now,
इज ऑडिबल, परफेक्टली
okay,
ऑडिबल.
okay, okay. Thank you. So, can you able to see the images over here now in this slide? Hello. Yeah. So these images are related to the specimen size or specimen generally used to identify or to test the tensile tensile properties of your polymeric material. So if you see the very left hand side image, it is nothing but the dumbbell size of specimen which is cutted using cut, or you can molded it using some specific type of mold. Okay, so this kind of dumbbell shape specimen is generally used to identify, or is generally used to test over this kind of stationary and moving heads to analyze the tensile properties. Okay, so how we can analyze the tensile properties using this kind of specimen or this kind of test, we will see in our next slide. Here you can see the actual testing procedure or actual testing images over here. So if you see here, two heads are been there. One is the stationary one. If you see this below, one is the stationary one head, or you can call it as a jaw. Okay, or if you see here, one clamp is present. In that clamp we clamped our plastic specimen. Okay, and this upper one is nothing but the moving head. We can call it as a moving head. Okay, so in the moving head is attached to the load cell. what is the work of load cell? Load cell, it generally measures the applied load, or we can say whatever stress have been applied over your sample, that can be measured by your load cell. Okay, so if you see in this image, the dumbbell shaped specimen have been attached or clamped to these both jaws of the machine, and the movable whatever the movable clamp, it is it is pulling up the specimen in upward direction. Correct? Can you able to see this? Yes. Okay. So if 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 it is clear to all of you, like how your tensile test or tensile specimens have been tested against the stress, and uh, how that specimen have been deform to its shape. Okay, that deformation of shape we will see in our coming slides. Okay, so what all kind of testings we can perform using this kind of machines. Okay, or you can say which machine is this? It is nothing but the universal testing machine. We generally call it as a UTM. Okay, over this machine, many kind of or you can say majorly all of the mechanical properties can be performed using this kind of machine. That's why it is called as a universal testing machine for materials, or you can say polymers. Okay, so first test we can perform using this machine is nothing but the stress strain behavior of your polymeric material, which is nothing but out of which we will get the tensile strength of the polymeric specimen. Okay, so second is like, as you can see in this image, first is like the tensile properties of your polymeric material. Then second, if you observe this image, okay, this image is showing the again the pulling of both the slides, okay, in opposite direction. But if you see, there is some yellow colors polymeric material have been stick over. It is nothing but the test for adhesives. Okay, have it is generally these two tests are generally using for adhesive performance, or you can say to calculate or to analyze the adhesive property of your or adhesion property of your adhesive materials, or you can say polymeric adhesives. Okay, so for that, first test which can be done is like the peel strength. Okay, that peel strength can be performed using, if you see the samples, the adhesive sample have been applied in between the two strips. Okay, and that two strips have been s- uh, that two strips have been pulled in opposite direction at 180-degree angle, if you see here. Correct, so this is nothing but the peel strength testing using your universal testing machine. Okay, so if you see the second image over here, in second image as well, if you see, the adhesive has been applied in between the two plates. Correct, can you able to see this? Yes. Hello. 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 Okay, so I think I should continue with this slide only. So if you see the second one, this is also the test which is generally used to determine the adhesive property of your adhesion properties of your adhesive materials. Okay, in that also, if you see in between the two slides, or you can see two plates, adhesive has been applied to stick the plates. Okay, and generally uh, if you pull that sheets, or you can say plates in opposite direction, it will create shear in between the plates. Okay, and that strength will, we can call it as a shear strength. Okay, that shear strength of adhesives have been calculated using, or have been tested using this universal testing machine, or you can say this kind of mechanical properties have been tested over here. Correct, So these are nothing but the tests generally perform on the adhesives as well as the very first test, whatever the tensile test given here, it will give the tensile strength of the polymeric material. Okay. So in this image, you can observe here one machine is there. This machine is nothing but the again universal testing machine. If you see this sample have been clamped over here, and the upper jaw, which we called it as a moving jaw, that moving jaw stretches that polymeric sample in upward direction. So simultaneously, whatever the load cell applied over that moving jaw, that calculate the force. Okay, if you see in this graph here, okay, this is nothing but the engineering stress, or we can simply call it as a stress to strain curve. If as we apply stress to the polymeric material, it will go upward in upward direction, and breaking after a certain point, that polymeric specimen will get break. Okay, so that point is nothing but the break point or breaking yield of the polymeric sample. Okay, are you getting what I am saying? Hello, 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 am I audible to all of you? I think my network connection is okay. Hello, 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 hello.
Hello.
Yes sir, I am clearly audible, no?
Yes, yes, sir.
Because uh,
Don't know why they have. Don't know why they have.
because I am not understanding that if they are listening or not, because no one is responding out of that. Five students are there. Hello.
Hello.
Yes, sir. Means can I continue or
Yeah, yeah. You can continue, sir. Don't worry about it,
because
sir.
okay,
If it is not there, we can continue our schedule. Otherwise, it is very difficult us to complete the entire thing.
yeah, because already I think 1 or 2 more days we have already extended.
Already extended. Yeah.
Yeah. Okay, so this is nothing but all of about the tensile test or tensile properties of the polymeric material. So here we have here we have given the standard size of your specimen, which generally used to determine the tensile properties. Okay, as I have mentioned, like dumbbell shaped specimen have been used, but according to various standards, the shape and size of your that polymeric specimen have been changed, and that shape and size have been presented in this slide. Okay, in various dimensions, that shape can be cut to test the specimen. Okay, so next is like the specimens. Next is like the specimen test speed. Okay, so if you see in this slide, the movement of your jaws have some specific speed to it. Correct. At some constant speed, it is moving to upward direction to stretch the polymeric specimen. So that speed also have been mentioned in your standards, or you can say whatever standard we are using to test this kind of property of polymer. So in that test speed have been also mentioned over here, correct? And also, as we have testing this kind of polymeric materials with UTM, that like universal testing machine, so minimum 5 samples for each polymer we have to test. because if suppose some sample get break at sudden instances, so in that case we can't consider the results over there, correct? So in that case we have to test other samples. So generally in standard as well they have mentioned like minimum 5 samples have to be tested for single polymeric material, because out of that we can average the results and we can present the results in that way. Okay, so number of test specimens that test at least 5 specimens for each sample. Okay, so this is nothing but the regarding the number of specimens as well as the specimen test speed of the material. Okay, then if you see what all kind of results you can observe in the test method, like what kind of polymer it is having, like if your polymer is behaving in what kind of properties, like elastic or plastic or some ductile nature. Okay, so how you can understand that part? So here we have some general representations to understand the type of material. Okay, so how we will identify that? So here nothing but the, if you see here, it is nothing but the elastic deformation, correct? What do you mean by elastic? Elastic is nothing but the property of material which generally uses, like if you stretch the material, it will get stretched or it will get deformed in a size, or it will get stretched. Okay, and after removing the force it will again regain its original shape. Okay, this is nothing but the property of elastic material, or you can say rubbery material. So that kind of deformation or that kind of property we can call it as a elastic deformation. Okay, so it will show this kind of graphs generally. Okay, so these materials we can call it as a elastic, means nothing but the reversible. As we have stretched the material, it will get stretched and it will change its size. Okay, as we have stretching it, obviously its length will get increased, and after removing this force you will return to the original position. Or if you suppose consider the example of rubber band, or if you stretch the rubber band by 2 hands. Okay, if you stretch it, your rubber band's length will get changed, or its length will get increased and thickness will get decreased, correct? So after that, if you remove the force, or if you again remove all the forces applied by your 2 hands, then again your rubber band will get its original shape. Okay, that's why it's it's called as a reversible process, or elastic means reversible thing. Okay, so this is all about your elastic deformation of polymeric systems. Okay, or the polymers, what polymer we can call it as a elastic, which regain its original shape after removing the applied force. Okay, so second is nothing but your plastic deformation. Okay, if you see here, three states have been given over here. Okay, if you see in very first step, which is nothing but the initial, the grains or whatever the material grains are presented in a very well arranged manner, correct? But after applying the force, your material will get deformed. Okay, but after removing the force, your material will not regain its original shape, but it is regaining some of the shape, or like some of the length it will get again to its, means it will try to regain the shape, but it will not regain the shape perfectly, correct? So that kind of material or that kind of property, it's called as a plastic deformation of your polymeric material. Okay, in that you will not get its original shape again. Okay, so that's why plastic means permanent. Okay, if you stretch the material, you will not get its original shape again. Okay, so this is nothing but the type of plastic deformation. Then the next to it, okay, the next to it, it is like permanent plastic deformation. Okay, permanent plastic deformation is what? It is nothing but again, if you stretch that similar kind of material with again some more force, so your material will transfer to the permanent shape change. Okay, its shape will get changed permanently. So in that way, you will get the permanent plastic deformation to your polymeric material. Okay. So if you see the graph over here, here some three type of limits have been given here. If you stretch your material till the force where I have mentioned the cursor here, if you remove the force from here, your material will regain its shape to the original. But if you again increase the stress, or we can say force to it, so it will move to this point where your plastic deformation is there. Correct? But after again applying the force, you will transfer that system to the permanent plastic deformation part. Okay. So this is nothing but all about the elastic deformation, plastic deformation, and permanent plastic deformation of polymeric material. Okay. Here, to better understand the part, we have presented here with the help of that dumbbell shaped material. Like if you start to start providing stress to the material at this point, if you see here the P point, it is nothing but the range in which you can consider your material is in a elastic, your material will show the elastic behavior till this point. if you again if you again apply stress from this point, your material will move toward the yield point. Okay, this is nothing but the yield point from where your material, if you apply the more stress, your material will shift to the permanent deformation. Okay, after shifting to the permanent deformation, if you again apply the stress, your material will go to the break point after applying some more stress to it. Okay, this is all about the elastic plastic or permanent plastic or breaking strength of your material by, or you can say overall tensile properties have been studied through this kind of test. Okay. So next is like the hardness of your polymeric material. So how we can calculate or how we can determine the hardness of polymeric or plastic material. So there is one test which is called as a drop test. Okay, it is nothing but the resistance to permanently indentation to the surface. Okay, so large hardness means resistance to plastic deformation or cracking in the compression. Okay, if you see here two images have been presented here. Okay, so this is nothing but the you can consider it as a metal ball which generally of 1 to 1000 grams. Okay, depending on your polymeric material, that weight have been changed. Okay, accordingly. Okay, suppose if you drop that ball with with some height. Okay, so your material will get deformed. If you can able to see here, kind of deformation have been seen over here due to the dropping of this kind of ball. Okay, so this is nothing but the indentation due to the dropping of the ball. Okay, which change the shape of your polymeric material. Okay,
Okay, sir,
so
your voice
this
is little slow.
hello.
Yeah, it is okay.
Yeah. So this kind of deformation have been occurred due to the dropping of your ball with some specific weight. Okay. So this is nothing but a measure of hardness. Your hardness of your polymer we can measure through this kind of test. Okay. The if you see like most plastics have harder in nature. If you see like increasing hardness, if you see the bar over here, the hardest material, as all of you know, that it is nothing but the diamond. Okay, diamond is the hardest material over here. But if you see like plastic, where plastics comes, it is nothing but the very less hard material, depending again upon the type of polymer it is. Okay, but generally plastic comes under this kind of category. Okay, so this is nothing but the hardness property or measurement of hardness of the polymer. Okay, by drop impact. Okay, so again if you can see here, this is nothing but the again hardness to determine the hardness of material. It is nothing but the charge by the impact to your polymeric system. It is nothing but the impact hardness. Okay, it is of again there are some types of impact. One is charpy and one is isod impact. Okay, so there are two types. If you see the this image over here, some cut have been made to your plastic material. This cut is called as a notch. Okay, these notch have been made over your polymeric material. Okay, to the upper side of that polymeric material, some impact have been provided using some bar. Okay, so that testing method, it includes that kind of impact. Okay, so how much impact is needed to break or to crack the material, that have been calculated using this test. Okay, so accordingly you will get the impact strength of your material, or you can say polymeric material, using this kind of test. Okay, so this all about whatever we have studied till now. It is all about the mechanical properties of the polymeric material, how that mechanical properties will get tested using different test methods. Okay, that methods have been described here. Like very first method we have studied is nothing but the flexural strength. Okay, in yesterday's lecture, in that also we have studied two type of flexural strength. One is like 3 point bending and second is like 4 point bending. Okay, after that we have started with like tensile properties or tensile test of the polymeric material, in which we have studied like behavior, different behaviors of your polymeric material against the tensile test. Okay, then after that we have studied the hardness, means how we can calculate the hardness of your polymeric material. Okay, using drop impact test. Then the last one we have studied is nothing but the impact properties of your polymeric material using Charpy impact test or ISOD impact test. Okay. So further we will move forward with the thermal properties of polymeric material. Okay, like how your polymeric material will behave in a in a different temperature or thermal conditions or heat conditions. So that we can study using this kind of testing. Okay, so in thermal properties we will see like very first that importance of thermal properties. Thermal properties plays a vital role in evaluating the product performance and processability characteristics of polymer. Then the thermal analytical methods monitor differences in some sample properties, as well as the if we increase or decrease the temperature of your temperature of sample, or between a sample and a standard as a function of added heat. Okay, these methods are usually applied to solids and the characterize the materials. Okay, to determine the thermal behavior, means behavior of polymeric material in presence of heat or thermal conditions. Okay, so what all kind of tests can be carried out to determine the thermal properties of polymeric materials that are listed here? Like like very basic methods are nothing but the heat deflection temperature, which is nothing but the HDT, and second is like Vicat softening temperature or Vicat softening point. Okay, so these are the two basic tests which can be performed to determine the softening point, or the we can say at least softening point of your polymeric material. Okay, then again if you see the advanced techniques, then in that thermal conductivity, thermal expansion, low temperature brittleness, flammability, melting point, glass transition temperature, then crystallinity, or crystalline point, crystallinity temperature of your material, then thermomechanical analysis. Okay, so out of which I think in day before's lecture, thermal transitions lecture, I think DMA, that is dynamic mechanical analysis or dynamic thermal analysis, have been you have been studied with which have been took by I think Jyoti sir. Okay, he has explained you the part of thermal analysis, some of the part of thermal analysis. Okay, but we will see again one by one to it. Okay, so types of thermal analytical techniques. So these all are the basic techniques. If you see the advanced thermal analysis techniques, the very first is nothing but the thermogravimetry analysis. Second is your differential thermal analysis. Then differential scanning calorimetry, which is nothing but the DSC. Then thermomechanical analysis, TMA. Then again, if you move forward for some advanced, again, some more advanced techniques, which are nothing but the dynamic mechanical analysis and dielectrical thermal analysis. Okay, out of which whatever the required, majorly required characterization techniques are there, that we will see in our lecture. Okay, so first of all, what do you mean by thermal transition of polymeric material? Okay, I think you have already studied about it, but we will see in a very short. Okay, what do you mean by thermal transitions of polymeric material or transition temperatures for polymeric material? If you see this arrow, you will see step by step temperature profiles, or you can say at what temperature your materials will perform in which manner. Okay, so if you start with a solid polymeric material, okay, if you start to heat the polymer, if you suppose if you have some polymeric substance with you, okay, and if you start to heat it, okay, what the first thing you will observe over there in that polymeric material? So it is nothing but the it will start to become soft. Okay, it will get soft at very first stage after providing the temperature or heat to the polymeric material. Okay, that point is nothing, that temperature we can call it as a softening temperature of softening point. Okay, that can be generally analyzed by your Weicat softening analysis, or you can say heat deflection temperature, HDT. Okay, if you move forward with that, again, if you provide some more heat to it, okay, more heat to that same material, or you can say plastic material, you will observe that your material is behaving like some rubbery type of nature. Okay, means it at that point your material is converting from hard to rubbery or flexible form. So that point or that temperature we can call it as a glass transition temperature. Okay, that point or that temperature we can call it as a glass transition temperature. And again, if you move forward by providing some more temperature to your polymeric system or polymeric material, so obviously after flexibility or after that rubbery behavior, if you add some more temperature or if you provide some more temperature to it, your your material will move to melt, to become a molten form. Correct, your material will start to melt. Okay, so that range or that temperature range where from where your material starts melting to completely melt, that range we can call it as a melting temperature. Okay, so again, if you want to complete the temperature profile of your polymeric material, if you again heat the material, then obviously after that you the polymeric material will start to degrade. Okay, but if you start to cool down the material after melting point, okay, if you start to cool down the material after melting point, if you reverse the process of heat or temperature after melting, so if you start to cooling, the very first temperature we will get is nothing but a crystalline temperature. Because what temperature we can call it as a crystalline temperature, which is nothing but from molten state when your polymer will again form solid. Okay, means whatever the polymeric chains or whatever the polymeric macromolecules will rearrange their structure to become a solid after cooling the sample. So that temperature at which your part will become solid again, that we can call it as a crystalline temperature. Okay, so this is all about the thermal transition of polymeric or transition temperatures of polymeric material, or you can say thermal behavior or thermal profiles of your polymeric system. Okay, so these all things can be tested or can be characterized using different testing methods. Okay, So that different testing methods, out of which we, as we have mentioned, like for softening point, there are two testing methods. One is like quicket softening analysis, and second is heat deflection temperature. Okay. And also for next temperature points, like differential scanning calorimetry has been used to determine the glass transition temperature, melting point, then crystallinity temperature, and the degradation temperature. Okay, that things can be degradation temperature have been measured by your thermal gravimetric analysis. Okay, this measure change in weight during heat or cooling. Okay, so these all kind of techniques have been used to determine the thermal behavior of your polymeric material. Okay, so in that also, the very first technique to determine the deflection temperature is nothing but, or we can say softening temperature is nothing but the heat deflection temperature. Okay. So what all things are there in heat deflection temperature, we will see here. Okay. So heat deflection temperature, it is defined as the temperature at which a standard sample bar of your polymeric material deflects zero point 0.1 inch under a stated load of either 66 or 264 psi. Okay, so this test have been used with some specific load, and if you see the dimensions of your polymeric bar which has been presented in that bracket. Okay, so what is the significance of this test, means what all things we can get, or all things we can understand using this kind of test. Okay, so significance in, it is like nothing but HDT, that is heat deflection temperature values, are used to compare the elevated temperature performance of the materials under specific load at the stated conditions. Okay, it is used for screening and ranking materials for short term heat resistance. Okay, you can identify the heat resistance, like short term heat resistance, using these kind of testings. HDT values do not represent the upper temperature limit for a specific material or application. Okay, because it will only provide the starting of your like softening point. Okay, the data are not indented for use in a design or predicting endurance at elevated temperature. So what kind of test methods or standards have been used that are given here? Okay, specimen size, what all conditions are required to test the specimen. Okay, so the apparatus which generally used to determine the heat deflection temperature is given in this image over here. Okay, if you see here, this where my cursor, red cursor is there, this blue uh, this blue specimen is nothing but the plastic specimen. Okay, and whatever the liquid present here, it is nothing but the oil, or we can say whatever this uh, container is nothing but the oil bath. Okay, that oil bath have been maintained with the increasing temperature range accordingly the requirement. Okay, this is nothing but a load applied over this bar, and this bar has been here indenter has been attached to it. Okay, and this gauge, depth gauge, have been provided here to calculate the depth or indentation of the polymer, indentation through the polymeric material at specific temperature. Okay, so this kind of apparatus have been used to determine the heat deflection temperature. Okay, in that, what is happening here, we will increase the oil temperature gradually. Okay, so at what temperature your load, or that material have been bent or indented using this load, that can be recorded in this gauge. Okay, so after deflection of zero point 0.1 inch, we record the readings of your temperature. Okay, so that temperature is nothing but your heat deflection temperature. So what is the procedure? As I have already explained that procedure with the help of that image, only the parameters are like adjust the load to obtain desired stress of 0.450 5 megapascal, or we can convert it as in a 66 psi or 1.82 megapascal. Heat the liquid, as I have told just now, heat the liquid heat transfer medium at a rate of 2 degrees Celsius per minute. Okay. And they record the temperature of liquid heat transfer medium at which the specimen has deflected the specified amount at specified fiber stress. Okay. So this is nothing but all about the heat deflection temperature, its procedure, mechanism, its significance, what are the sample requirements, okay, and the deflection requirements of the samples. Okay. Then next is like results and conclusion of like what kind of results we will get using this kind of test. Okay. So obviously we will get the heat deflection temperature, that is the temperature at which your polymeric part will get deflect by zero point 0.1 inch. Okay. So that can be presented accordingly. So which kind of factors will influence the heat deflection temperature test? So HDT of unannealed, or you can say heat treatment specimen, is usually lower than that of annealed specimen. Then specimen thickness is directly proportional to the HDT. Obviously, if your thickness is more, your heat deflection temperature will get increasing slightly or accordingly the your thickness. Okay. Then the higher the fiber stress or loading, lower the HDT. If you're in your composite system, if you are having composite system, in that composite system, if your fiber loading of the fiber or fiber stress is more, so in that case your HDT will get. Okay. So injection molded specimens tends to have a lower HDT than the compression molded specimen. It is again depending upon the packing of your polymeric system. Okay. Accordingly, the packing density, your HDT will get changed of same material I'm talking about. Okay. Then compression molded specimen are relatively stress free. Okay. So these kind of factors are generally affected to your heat deflection temperature. Okay. Here we will just take break of 5 minutes and we will restart the lecture again. Okay. Hello. Hello. We will restart the lecture now again. Okay. Let me share the slides first. So till now we have studied about the heat deflection temperature or HDT of polymeric substance or polymeric material. So the next test for the polymer is nothing but the Wickett softening point or Wickett softening temperature. Okay, the test is defined as the temperature at which a flat-ended probe with nearly size or nearly dimension of 1 mm square cross section, which penetrate through the plastic specimen 2.4-inch depth. Okay, at specific temperature I'm talking about. Okay, so at some temperature, if suppose some probe or you can say flat-ended probe have been penetrates the plastic specimen with 0.04-inch depth. So that temperature we can generally call it as a Wickett softening point. Okay. By using this kind of test, we find out the softening temperature of softening point of the polymeric material. Okay. So what is the significance of this test? It is nothing but the data obtained by this test method may be used to compare the heat softening qualities of thermoplastic materials. Okay. Means at what temperature your material will get soft or what softening qualities your plastic material or thermoplastic material is having. Okay, so this test method is useful in the areas of quality control, development, and characterization of plastic materials. Okay, so in detail we will see how this test and what test methods have been used, specimen size and conditioning of the that specimens. Okay, so generally ASTM D1525 process have been used to identify the Wickett softening point of the polymeric material. Okay, so test specimen is having the specimen shell flat between 3 and 6.5 mm thickness and at least 10 by 10 mm in area. Okay, so this kind of specimen or specimen dimensions can be used to test the polymeric material with Wickett softening point. Okay, conditioning is nothing but that we can keep that specimen at nearly 23 degrees Celsius at 52 or 50 to 55 percent of relative humidity. Okay, for nearly 40 hours or less than the 40 hours of time. Okay, so a minimum of two specimens shall be used to test each sample. Okay, so this is nothing but the test method, specimen, and conditioning of the samples. Okay, so if you see what kind of apparatus have been used to identify the sorry, Wickett softening point is nothing but like similarly as in HDT, we are going to use here oil bath. Okay, and that oil bath again we can have the setup like we can increase the temperature of oil bath gradually. Okay, so if you see here again one penetration rod is there with flat tip. If you can see here, indenting tip is present over here. Okay, and in this slit we have kept the polymeric sample. Okay, on that polymeric sample we insert the tip on the surface of that polymeric sample and we are applying the load. Okay, and if you see here the depth gauge again similar to HDT have been presented here. Okay, so after increasing the temperature of this oil bath, obviously your polymeric material will get soft as we increase the temperature. Okay, so the temperature at which your tip, this is indenting tip, will reach the size of like 0.4 inch, as we have mentioned here, 0.4 inch depth. That temperature we recorded as a Wickett softening point. Okay, so this is nothing but about the test and test procedure. If you see here, the similar procedure have been mentioned here. to prepare the immersion bath, or we can say oil bath, so that the temperature of the heat transfer medium is between 20 and 23 degrees Celsius at the start. Okay, that we have to place the specimen which is at room temperature on the specimen support. Okay, gently lower the needle rod without the extra mass so that the needle rests on the surface of your plastic specimen, and then we can hold it in a position, a similar position. Okay, so position the temperature measuring device so that the sensing end is located within 10 millimeter from where the load is applied to the surface of the specimen. Okay, as we now the next step is like the lower the assembly into the bath and apply the extra mass required to increase the load on the specimen to like 10 Newton. Okay, 10 to 50 Newton. Okay, this is the two loading conditions for the wicket softening point. And after a 5 minute waiting period, set the penetration indicator to 0. Okay, as whatever the indicator is presented here in depth gauge, that we will set to the 0 before starting the test. Okay, then we have to record the temperature of the bath when the needle has penetrated 1 mm into the test specimen. Okay. So what kind of results we can get using this test? We have already discussed, like Weigert softening temperature is expressed as the arithmetic mean of the temperature of penetration of all specimens tested. Okay. If the range of penetration temperature for the individual test specimen exceeds 2 degrees Celsius, okay, record the individual results and repeat the test again. Okay, using the same process. So this kind of results can be obtained using the Weigert softening temperature. Okay. So next is again one kind of thermal testing, which is nothing but the thermal conductivity of your polymeric material. So what is there in thermal conductivity? So thermal conductivity is nothing but the rate at which heat is transferred by conduction through a unit cross section area of material when a temperature gradient exists perpendicular to the area. Means it is nothing but the heat transfer through the polymeric material per unit area. Okay, per unit polymeric surface area. Okay, means at specific surface area how much heat can be transferred through your polymeric material, that can be calculated. Okay, so the coefficient of thermal conductivity K is defined as the quantity of heat that passes through a unit cube of the substances in a given unit time when the differences in temperature of the two phases is 1 degree Celsius. Okay. Mathematically, the thermal conductivity is expressed as follows. The formula have been given here, in which Q is nothing but the amount of heat passing through a cross section. Okay, cross section means that cross section area, that A causing a temperature difference, whatever the A, that cross section area is causing the temperature difference of delta T, which is nothing but a T1 and T2. Okay, that is nothing but the two surface temperatures of both the surfaces, like front surface or back surface, you can consider of that surface area or that cube. Okay, so T is nothing but the thickness of the specimen. Okay, K is the thermal conductivity constant, typically measured by some unit, like indicates the material ability to conduct the heat energy. Okay, which is generally provided in many of the literatures. Okay, so what is the significance? What is the use of this kind of test, that is thermal conductivity? The thermal conductivity is particularly important in applications such as headlight housing, pot handles, and hair curlers that requires thermal insulation or heat insulation to it. Correct? Computerized mold filling analysis program requires special thermal conductivity data derived at higher temperature than specific by the most test. Okay, so this kind of applications require generally to identify that uh, what kind of means what temperature or what conductivity is there in that polymeric material, or what heat conduct how that material is heat conductive at what level. Okay, that kind of identification we can perform using this kind of test. Okay, This is nothing but the test method and specimen dimensions have been provided according to the ASTM standard, that is ASTM D177 and ISO 2582. Okay. The apparatus is nothing but the broadly of two different categories. Okay, type 1 is nothing but the low for low temperatures. Okay, and type 2 is nothing but for the high temperature range of your polymeric material. Okay, it generally consists of heat units, gap measuring areas, then unbalanced detectors, cooling units, sensors for measuring temperature difference, then clamping forces, measuring systems. Okay, if you see here, this is nothing but the general representation of your of your apparatus for thermal conductivity measurements. Okay, it generally, if you see, many plates have been present over here. Okay, to to analyze the sample. If you see, samples have been placed in between. Okay, so after that sample, you can see auxiliary heaters have been provided, and after that heaters, cooling plates have been provided. Okay, and to hold the system, insulations have been provided to restrict the dissipation of heat. Okay, this is nothing but the apparatus for the test. Okay, so this procedure we already have discussed. Okay, this is nothing but the formula which we have discussed. Accordingly, we can calculate the thermal conductivity of your polymeric materials. Okay, so what kind of factors affect the thermal conductivity of polymer? It is nothing but the crystallite or crystallinity present or difference in your polymeric material, which is highly like crystallites have higher conductivity. Okay, as the density of the cellular plastic decreases, the conductivity also decreases up to a minimum value and rises again due to increased convection effects caused by a higher proportion of open cells present in your polymeric system. Okay, so next property of thermal testing is nothing but the thermal expansion, or you can say coefficient of linear thermal expansion. Okay, so generally, if you see, after heating the polymeric material, it starts to expand. Okay, generally many of the polymers, if you start to heat it, it start to expand. So accordingly, to understand the property, this kind of test have been performed. It is nothing but to measure the change in length per unit length of a material per unit change in temperature. This is nothing but a general principle as I have explained you. Okay. So mathematically, these temperatures between T1 and T2 for a specimen of length L at the reference temperature. This is nothing but a general formula for the calculation of thermal expansion or coefficient of linear thermal expansion. Why we use this kind of test, or what is the significance of this test, is like determine it. This kind of test generally determines the rate at which a material expands as a function of temperature, as I have explained. Okay, the higher the value of this coefficient, the more a material expands and contracts with temperature change. Okay, then plastics tends to expand and contract anywhere from 6 to 9 times more than materials that are metallic. Obviously, if you try to try same thing with metals, it can't perform similar way. If you have plastics with you, if you try to expand and then again contract, then again expand, contract, these kind of things we can repeat again and again with the with plastic materials, but not with metallic. Then the thermal expansion differences develops internal stresses and stress concentrations in the polymeric system, which allows the per premature failure to occur. Okay. So what kind of test methods have been used here? This is nothing. This kind of tests have been analyzed using the standard test method as STM D696. Okay. The test specimen sizes and conditioning of the specimens have been presented over here. Okay. So this is nothing but the general representation of apparatus used to measure the heat expansion. Okay, linear heat expansion. This is the general procedure. Okay. So what kind of factors are generally affect the thermal expansion of your polymeric materials, which are nothing but the thermal expansion is substantially affected by the use of additives, correct? Suppose if you are adding additives to impart some properties or impart some strength to your polymeric material, that generally affects the thermal expansion, or you can say that restricts the thermal expansion of your polymeric material, especially fillers. Okay, and the loading of or weight percent loading of the fillers, which lowers the coefficient of thermal expansion. Okay, because that creates some more packing like material, or packing is uh, greater in that case if you use fillers in a low, or loading of fillers in much percent. Okay, then as I have explained you about the thermal transitions or transition temperatures of polymeric material, that all kind of transition temperatures can be tested using differential scanning calorimetry method. Okay, DSC measures the heat flow into or from a sample as it is heated, cooled, or held under isothermal conditions. Okay, so application of DSC includes characterization of like polymers, fibers, elastomers, composites, films, pharmaceuticals, foods, and cosmetics. Okay, so what all things DSC can provide us as a testing of polymeric materials. So we will get these all things using this DSC. The first of all is nothing but the glass transition temperature, which is nothing but the important factor for your polymeric material testing. Okay. Second is melting point, then crystallization times and temperature, heat of melting and crystallization, then percent crystallinity is present in your polymer, means at what extent your polymer is crystalline, that can be identified using your differential scanning calorimetry. Then heat capacities, heat of curing, and thermal stabilities of your polymeric material. Okay, so these all kind of tests can be performed or can be get using your DSC analysis. Okay, so this is nothing but the general representation of the DSC apparatus. Okay, which generally contain a furnace, closed furnace with neutral gases present in it, generally the nitrogen we can say. Okay, then temperature senses, then differential senses. Okay, so for this test, we generally use aluminum pans. Okay, in that also we used sample in a one pan, and one in is a blank pan, which we called it as a reference pan. Okay, and in second pan we insert the polymeric sample, which we generally use or which we have to study. Okay, so the this is nothing but the setup for your DSC. Okay, so what procedure is there? So DSC apparatus consists of two sealed pans, as I have explained now. The pans are heated or cooled uniformly, while the heat flow difference between the two is monitored by the sensors. Okay, this can be done at constant temperatures, or you can say isothermal, but is more commonly done by changing the temperature, means the varying the temperature. If you are like if you want some like as we have mentioned that transitions of thermal transitions of your polymeric material, then you gradually or increase the temperature, so you will get the first you will get the glass transition temperature, then melting point or melting temperature, then if you start cooling it you will get the crystallinity temperature or crystallization sites, correct? So accordingly you will change the temperature. So changing the temperature at a constant rate called temperature scanning. Okay, the instrument detects differences in the heat flow between the sample and reference, that is nothing but a blank, and plots the differential heat flow between the reference and sample sets, okay, as a function of temperature. So if you see, as we have already seen the flow of the transition systems or transition temperatures. Okay, so if you start heating it, you will first get the TG is nothing but the glass transition temperature. Okay, then the melting temperature. Okay, in a heating cycle, and whatever the crystallization temperature is given here, this we will get in a cooling cycle. Okay, so results and conclusion for DSC analysis is nothing but the DSC thermograms provide an elaborate study or elaborate picture of various transitions, as I have already mentioned, in a polymer, the degree of crystallinity in a polymer, then the specific heat can be determined using this kind of testing. Any side reaction or, for example, cross-linking, thermal degradation or oxidation, that can also be reported and the reaction identified if possible. Okay. So what all factors can be affect to DSC is nothing but the addition of fillers. Obviously, if you are adding the fillers, it will change the properties of your polymeric composite. Okay, that addition of fillers affect the transitions in DSC. Then previous thermal history of the sample also affect the DSC transition. Like if you have heated or cooled that polymeric sample previously 2 3 times, then obviously its thermal behavior will get changed accordingly. Its according to its rearrangement of polymeric chains. So there should be proper contact between the samples and pans. This is nothing but again the third factor. So the next test, or we can say next thermal property of or the test for the polymeric is nothing but the TGA. That is nothing but a thermal gravimetric analysis. Okay, just give me 1 minute. Okay. Hello. Okay. So there is some issue with my PPT. Okay. Okay. So next part is nothing but the thermogravimetric analysis, or we can call it as a TGA. TGA is generally used to determine the thermal stability of your polymeric material as well as the thermal degradation behavior of the polymeric material. Okay. So in that also, if you see, generally TGA, the principle of TGA is nothing but the changes in weight of the specimen, okay, is recorded as the specimen is heated in air or in a controlled atmosphere such as nitrogen. Okay, so what exactly happens in TJ we will see. So thermogravimetric curves provides information regarding the uh, regarding the polymerization reactions, the efficiency of stabilizers and activators, the thermal stability of final materials, and direct analysis. It also provides a general technique to determine the amount of highly volatile matter, as it will evaporate under some temperature conditions, and medium volatile matter. Okay. This test method is useful in performing a compositional analysis in polymer. This test method is also applicable to sol solids and liquids. These are nothing but the significance of the thermogravimetric analysis. So what exactly happens in this test that we will see here in this slide. Okay. So generally this equipment involves generally this type of instruments involves some highly sensitive balance. Okay, this is nothing but the very highly sensitive balance which is generally attached with that a pan is attached with that balance ceramic pan, and that ceramic pan we generally keep the polymeric material with some at in a inert atmosphere or a air in a air atmosphere. Okay, and this pan we insert in, if you suppose consider these red lines are nothing but the furnace. Okay, we insert this pan or we hang this pan in a furnace, and that furnace temperature we gradually increases. Okay, the temperature we gradually increases. Okay, and that after increasing the temperature, your polymer starts to lose the weight. Okay, so that weight loss have been recorded by increasing temperature as a result. Okay, so this is carried out in thermobalance, permitting the continuous measurement of sample weight as a function of temperature and time. Okay, so these are nothing but the simple principle of working of your thermogravimetric analysis or TGA. Okay. So what is the procedure over here? As I have explained in short, we will see the procedure for it. Okay. This is nothing but the established the inert and reactive air gases at the desired flow rate. Okay. So hello, hello. Yeah. So if you see, we keep specimen sample with like in between 10 to 30 mg into the pan, carefully place it in the specimen holder. Okay, that position the specimen temperature sensor, enclose the specimen holder, then record the initial mass, whatever the initial mass we have taken, like if it is in between the 10 to 30 mg, that whatever mass we will take that have been recorded. Okay, and we start the heating program within the desired temperature range. Okay, and the range of temperature that polymeric materials we can test once a mass loss plateau is established in the range of 600 to 1200, we can keep that temperature from this, from room temperature we can test it the part till 600 or highly till 1200 degrees Celsius, depending on the material, or we can say depending on the polymeric material switch from inert to reactive environment. Okay, so what all kind of factors have been affected to your thermal or thermogravimetric analysis or TGA is nothing but the oil filled elastomers have such a high molecular weight of oils and such a low molecular weight polymer content that the oil and polymer may not be separated based upon the temperature stability. Okay, this is nothing but the material related factor which affects the TGA. Okay, then second is like ash content materials or metals are slowly oxidized at high temperature and in an air atmosphere, so that their mass increases, okay, or decreases with time. Under such conditions, a specific temperature or time re- region must be identified for the measurement of that component. Okay, then third factor is nothing but a polymer, especially neoprene, or you can say rubber type of, or acrylobutadiene rubber (NBR), carbonized to considerable extent, giving low value for the polymer and high rubber values. Okay, then the last factor, which is nothing but the such as the calcium carbonate releases CO2 upon decomposition at interference, is dependent upon the type and quantity of the pigment present in your polymeric system. Okay, so these all things are nothing but the nothing about the thermal properties or thermal testings of your polymeric material, in which we have seen till now, like starts from thermal expansion, thermal linear expansion of polymeric material, heat deflection temperature, then wicket softening point. Okay. Then again start with some advanced techniques like DSC, differential scanning calorimeter, by which we can identify thermal transitions of your polymeric material, in which like glass transition temperature, melting points, crystallinity temperature, crystallinity regions, heat flow, heat capacity of polymeric materials, that we can identify using DSC or dynamics like dynamic scanning calorimeter. Okay. Then the last one we have observed here, TGA thermogravimetric analysis, in which we can study the thermal stability as well as heat degradation or degradation of your polymeric material. Okay. So the next type of testing we will study is nothing regarding the flammability properties of your polymers. Okay. Generally, if you know about the polymer, the general thing means the generalized thing is like polymers can burn. Okay, if you start to give flame to the polymer tends to burn, because if you see, most of the polymers contain the hydrocarbon chains in it. Okay, and the hydrocarbon system is nothing but the flammable one. So most of the polymers are flammable in nature. Okay, so that flammability properties can be studied or can be tested using some of the techniques. Okay, so there are two techniques generally used to characterize or to test the flammability properties. One is like the burning test, or we can call it as a UL94 test, as a like vertical burning test, generally called it as. And second is LOI. LOI is nothing but the limiting oxygen index. Okay, that these two tests we will see in detail in further slides. Okay, so very first test, as I have like mentioned just now, it is the vertical burning test. We can call it as a UL94 test. Okay. So in UL94 test, what exactly we can perform? We just hang the polymeric sample or polymeric film or polymeric component in vertical direction. Okay, towards the vertical downward direction. Okay, and flame. If you see here, this yellow color, blue yellow color flame, the flame have been applied at 45-degree angle. Okay, so this kind of test is called as a vertical burning test, or you can call it as a UL94 according to its names. Okay, and the readings have been mentioned according to the burning characteristics of your polymer. Like if you can observe, if you burn the polymer, some of the polymer starts burning and it will take up the fire in a very rapid manner. Correct. Some of the polymers drip into some droplets if you start to burn it. Okay. Some of the polymers are like it it restrict the flame. Some of the polymers are like that polymer restrict the flame due to its flame retardancy property. So that all readings or that all observations can be presented in this kind of readings like V0, V1, and V2. That what all things are included in that readings we will see further slide. Okay. So these are nothing but the generalized images of the vertical burning test. If you can observe, see here we have hanged some polymeric materials in a vertical manner, and we have provided flame to it in 45-degree angle. Okay. After burning, if you see, it catch up the flame, catch up the fire, and if you see in this last picture, that drip, that polymeric material drip down with the flame. If you can able to see this part. Okay. So there are again, depending on the applications. Okay, there are different type of flame test. Like we have studied vertical burning for polymeric samples or hard samples. Okay, if you are having sheet, then we can use horizontal burning as well. Or if you are having some blocks like paint blocks or something, so for that we can use surface burning test. Okay. You can observe here for vertical burning, there are some readings provided here, as we have seen here, V0, V1, and V2. What that reading indicates exactly, V0 is nothing but the retardation of your flame. That means your polymeric material does not pick up the flame. it will restrict the flame. That kind of reading we can call, we can cover it in a V0 reading. Okay. Then V1 is nothing but a good, which is will start the flame, but after some time it will reduce the flame or it will retard the flame. And V2 is nothing but the dripping of your flame. Like if you see in this last picture, whatever the polymeric material, burning polymeric material, it drips down into the droplets of flame. Okay. So this is nothing but all, this is all about the burning characteristics of your polymeric material. The next, like second testing for flammability of polymers is nothing but the limiting oxygen index. Okay. So if you know,
In the flammability, what about that? If thermoset plastic is done, it will not drip down or it will not do no. In that
yes,
case,
can,
it will burn off. So this UL 94, is there only these much limitations, or is there any other things which can be done like
yes.
V1, V0, V1, V2 only is there, or something else can be the comments given for the tests?
Yeah, if your thermoset material is in the form of, like if you see here this kind of strips, can you observe these strips? Okay, if this is in that material is present in that kind, okay, then you have these three readings with you. Okay, these three readings can present your flame type or you can burning type. Okay, but if your thermoset material is presented in a coating form, okay, thermosets are generally used for coating purpose, correct? So if your thermoset material is coated on some surface, like suppose if you are having some block and that block you have coated your thermoset material as a coating, okay, so that coating you can't burn using the vertical burning test. Okay, so in that case what you can do is like you can apply the frame on the surface of that coating. Okay, and after that reading after that burning you can take the readings accordingly. Okay, similarly if you are having film or some kind of material, then in that case you can burn it horizontally. Okay, because if you burn the film vertically it will catch up the flame very fast. Okay, so accordingly applications or according to your type of polymeric materials, the test have been divided. Okay.
But this 3 minutes to burn a 4 inch, that is under conditions what we are giving. But
Yeah,
comments like UL 94, 95, V01, you told if it is in this condition, we can give that instead of writing that all the commands. V0
yeah,
means
V0 means whatever this is the standard format, like whatever the statements provided here. Okay,
some.
these statements these statements are present in that standard. Whatever the standard is there for UL94, in that standard these statements are there. Like for V0, vertical burning stop, if burning stop within 10 seconds. Okay, whatever the flame we are giving to your material, if that burning will stop within 10 seconds. Okay, after two applications of 10 seconds each of the film, and no dripping. If you see here this kind of dripping, can you observe this?
Yeah,
If no
yes.
dripping is there and flame is stops within 10 seconds, then we can give V0 rating to it. Okay, these all are nothing but the ratings, V0, V1, V2. These are the ratings to your flammability test.
Only for vertical, no?
Vertical burning.
But what about the this one? UL you are telling now for that what is the comment? That comment
Yeah, it is. Yeah, that comment are generally present in their standards. Okay, but for polymeric we generally use this kind of test. Okay, we prepare the samples accordingly. If you see the sample here, this is the sample specimen. Okay, but generally this whatever I have told, this is generally for coatings.
okay,
Okay, this is generally for coatings, not for polymers.
okay.
For
But
polymers we generally use vertical burning test.
okay. And the last films is even the covers also comes under this, no poly covers.
Yes, yes, yes.
Okay, for that, what is this this thing comments like instead of V0, V1, V2, what there we have to write?
Yeah, if it is having the thickness like your polymeric material, then obviously the readings are like V1, V0, V1, and V2. But the thickness is less, then the comments are, we can write down the comment as per the observations. Okay, for horizontal burning test.
What is good, what is bad, and what is
Yeah, that we can observe. Like if your flame is like, suppose your flame is stops within 20 seconds, then accordingly you can write down the observations that after mm, after providing providing flame for 10 seconds. Okay, after that, if your material is stopping the flame or burning stops within 15 seconds, so according you can write down the observations. Okay, if your material is dripping, okay, if you see here in V2 rating, it is like dripping is there, correct? So accordingly you can write down the observations for that test. Okay,
Mhm. Okay,
it
sir.
all depends upon the visual observations which will get you after the burning. Okay.
Okay. Okay,
Yeah.
sir.
So next is nothing but the limiting oxygen index. Okay. So this is the generally the standard method to identify the flammability of your plastic materials or polymeric materials. Okay. So what is main thing in limiting oxygen index, means why we are using limiting oxygen index? What do you mean by limiting oxygen index, first of all? Okay. So if you see, like in general, I'm telling about, if you take a paper, okay, if you take a paper and you try to burn it in an atmospheric condition, if you ignite the paper, it will get burned, correct? Okay, so your paper will get burned in your atmospheric condition. Why that paper will get burned? Can you tell me? Do you have any idea about like why that paper will get burned?
Because it's a solid fluid, it's a solid combustible material, and oxygen is also available. So
Yeah,
once it
that
catches
that
fire,
that that is the main reason that oxygen is present in your atmosphere. Correct?
yes,
Oxygen at what percent oxygen is present? 21%. Correct?
yeah.
Atmospheric percent of oxygen is nothing
Sir,
but your,
your voice is feeble, sir.
hello. Now it's
No,
clear.
yeah,
Yeah.
okay.
Your atmospheric oxygen is 21%. Correct? Suppose suppose if you have a container in which no oxygen is there and you are trying to burn the paper, can your paper will get burned? Yes, without oxygen. Hello,
Go on, sir.
it will not get burned. Correct. So the same scenario is with this, like in what content of oxygen your polymeric materials will restrict the film. Okay, so that things we can study using this limiting oxygen index. Okay, the minimum concentration of oxygen that will just support flaming combustion in a flowing mixture of oxygen and nitrogen. Okay, because atmosphere contains 70 to something percent of your nitrogen and then oxygen, correct? So that's why this test is generally performed in the combination of oxygen and nitrogen mixture. Okay, a supported specimen is ignited with a pilot flame, okay, which is then removed. Okay, if you see here, chamber is there. In that chamber only the mixture of oxygen and nitrogen gas is there. Okay, we will adjust the percent of oxygen accordingly. Okay, if suppose your polymeric material is flame retardant, okay, it retards the flame very in a very good percent. Okay, suppose then we will increase the percent of your oxygen over here. Okay, if suppose at 25% of oxygen as well, your flame is getting retarded or your flame is getting stopped. Okay, then it is a good anti, you can say anti flame or you can say flame retardant. Okay, your polymer is good flame retardant. If you are, again, if you increase the flame if you increase the oxygen percent, like if you increase the oxygen percent till like 28%, okay, and then at 28% suppose your polymeric material will get burn or will get start flaming. Okay, then it is not a good percent of oxygen for your material. So
Percentage 28, it is the volume inside, or how we call it as percentage, sir?
volume, if suppose this is the 100% volume of your system, okay,
Okay.
whatever the chamber is there, then it is 28% filled by your oxygen, and what are the remaining percent, it is of your nitrogen.
Okay.
Okay, so at what maximum oxygen content it will restrict the flame, that percent is called as a LOI, or limiting oxygen index. So as much as high the LOI, that much your material is flame retardant. Okay, have you
Uh,
understand the test?
yes, sir. As much
Yeah,
it will continue to burn to certain level, or it is only the fire when
it
it
will it
catches.
will it will it should retard the flame.
Okay.
Okay, at that percent it should retard the flame. Okay,
Okay. That 26% of oxygen we have given, but how we know that 26% of oxygen is consumed
yeah,
and
that, yeah,
stopped?
it is not a consumed, that that percent of oxygen is present in your chamber, that is the adjustment of that instrument in it. Okay, you
That
have that, yeah,
you have given
you have
26%.
that adjustments that you can provide the 20, that readings are there over there.
No, you have given 26% of oxygen and nitrogen required percentage also is given and it is filled, understood. Once the
Yes,
fire is given, from
yes.
the fire it's burning. So only the oxygen 26% is completed and now it is stopping. Now how we will come to know?
See, that adjustments are provided over that instrument. Okay, whatever
Okay.
the chamber is filled with, that filled with continuous gas connection. Okay, if suppose for burning some oxygens have been utilized, then again that filled with that oxygen, that chamber. Okay, so that arrangements are there in that instruments.
Okay, okay.
Okay,
This is a procedure only. Okay.
yeah, this is nothing but the procedure to understand the test method. Okay, so
Okay,
this
understood.
is the second method of to identify the flammability properties of your polymeric material. Okay, so these are the test specimen sizes. Okay, sample preparation of limiting oxygen index. Okay, so this all about the flammability properties of your polymeric material. Okay, so let us start with electrical properties. Okay, electrical properties of polymers. Okay, what do you think? What kind of electrical properties can be there for polymeric systems? Polymers are electrically stable, or what means it can be a good thing for electrical, means electrical flow, or not? Okay, so generally polymers are considered to be electrically what? So generally polymers are inherently electrical insulators, correct? Which insulates the electric, or which retard the electrical flow, okay, or electric flow. Okay, so polymers are inherently electrical insulators. So they can be made to conduct the electricity by simply modifying the base material with proper additives like carbon black. If you use like carbon black or polyacrylonitrile, or you can say some graphene oxide in that way, so by using this kind of additives you can make your polymer conductive. Okay, so you can conduct the electricity to your electricity by simply modifying the base polymeric material. Okay, so what all kind of properties are there for measuring the electrical properties using this test? So tests are like dielectric strength, dielectric constant, dissipation factor, volume and surface resistivity, as we have seen in thermal analysis as well. Surface resistive, thermal resistivity, and surface thermal resistivity. Similarly, here also volume and surface resistivity, which is in terms of electrical test. Okay, so very first is nothing but the volume and surface resistivity of your polymeric material. Okay, the most desirable characteristics of an insulator is its stability, or is its ability to resist the leakage of electrical current. Okay, whatever the insulation we prepared on the electrical wires, so what characteristics it should have? It should not it should not have any leakage of the electrical current. Okay, The higher the insulation resistance, the better the insulator. Okay, the insulation resistance can be divided into volume resistance and surface resistance. Okay, first of all, what is volume resistivity? Volume resistivity is nothing but the total volume, okay, volume of the, or you can say volume resistance in ohm, okay, per area of the electrode contact with the test specimen, okay, and the thickness, okay. So volume resistivity is nothing but the potential gradient divided by the current density. So this is nothing but the sum of the numbers for that readings for the volume resistivity for different polymers have been given here. Then what do you mean by surface resistivity? The surface resistance of a material is defined as the ratio of the direct voltage applied to the electrodes, okay, to that portion of the current between them, that is primarily in a thin layer of moisture or other semiconducting materials that may be deposited on the surface, okay. This test method is generally used the ASTM D257 standard. Okay. Temperature and humidity inversely affect the resistivity of the material. Okay. Here we can observe the test specimen size, that is nothing but the 110 millimeter diameter disc with 3 mm of thickness. Okay. What what is the significance of this test? Means what we will get using this test? It is nothing but that this test measures the ability of current to flow over the surface of material. Okay. Then the second is like nothing but the surface resistance is the ratio of the direct voltage, as we have already the electrodes to the portion of the current between them, which is primarily in thin layers. Okay. Then volume resistivity is a property of the material. Surface resistivity is the measure of the susceptibility of the material to surface contamination. Okay. Then what is the dielectric strength? Okay, dielectric strength is nothing but the, when suppose an insulator is subjected to increasingly higher voltage. Okay, suppose some insulator is subjected to increasingly high voltage, it eventually breaks down and allows the current to pass through it. Okay, at the voltage at which the specimen breaks down, that voltage you can call it as a breakdown voltage. Okay, the voltage reached just before it breaks down divided by the thickness of the sample is known as the dielectric strength of the material measured in volts per million. Okay, so this is about the dielectric strength of the polymer. Then some dielectric strengths have been provided here for different polymeric materials. Okay, these are the resistivity, or we can call it as a dielectric constants. So dielectric constant is nothing but the dielectric of an insulating material is defined as the ratio of charge stored in the material when placed between two metallic plates to the charge that can be stored when the insulating material is replaced by air. Okay, it is nothing but the capacity of your polymeric material to store the electrical charge in it. Okay, so dielectric constants of various polymeric materials have been presented over in this table. Okay, and the last one is nothing but the arc resistance. Arc resistance is the ability of a plastic material to resist the action of high voltage. Means in at how much in how much content that polymeric materials resist the high voltage, that can be calculated using the arc resistance. Okay, it is defined as the time required for a given electrical current to render the surface of the material conductivity because of contamination of by arcing. Okay, this is nothing but about the arc resistance of the polymeric material. These are some numbers or those arc resistance given for the different polymeric materials. Okay. Then I think the last properties measurement is nothing but the optical properties of your polymeric material. What do you mean by optical properties? Okay, so whatever you have mentioned, like transparency of polymer, haziness of the polymer, that transparency, haziness, or the uh, this kind of properties, we can call it as a optical properties of the polymeric material. Okay, optical properties are nothing but the in that what all factors can be considered. It is nothing but the refractive index, light transmittance and haze, color and gloss. Okay, these all properties can be covered up in your optical properties of polymer. Refractive index is nothing but what refraction of your light rays through your polymeric system, which can generally called as a refractive index. Okay, light transmittance and haze. Light transmitter means whatever the transparency we talked about now of polymeric material, which is nothing but the transfer light transmittance through your polymeric material. Okay, so many of the optical properties are closely related to the electrical properties of the material, but as well as we shall see, other factors also come into the picture when dealing with the optical properties. Optical is nothing but the operating in or employing in the visible part of the electromagnetic spectrum, or we can call it as a relating to sight, especially in relation to the action of light. Okay, just a minute. Okay, so the simple picture starts uh, by considering the ray, or we can say light of an electromagnetic waves of a single frequency entering in a medium. Medium is nothing but your plastic material or polymeric substance from vacuum. This could be reflected, transmitted, or absorbed. Okay, you can see, you can observe here, if your material reflects the light, it is nothing but the reflection. The reflection is generally observed in mirror kind of material. Okay, then refraction is nothing but the your light ray pass through the material, but somewhat its direction deflects. Okay, that deflection in direction, and after that it will emits the part. Okay, that deflection in substance of light, deflection of light, we can call it as a refraction. Okay, and if your whole light get absorbed by the polymeric system, then we can call it as a absorption. Okay, then how you can calculate the refractive index, the formulas have been given here. Okay, and with the constants and all. Okay, so this is nothing but some refractive index of specific polymers have been presented here. Okay, the values of refractive index for various plastic materials. Okay, then this is nothing but the this is nothing but the luminous transmittance and haze calculation. Haze means what? If your material having less transparent, or you can say whitish color or whitish thing in it, or you can say less transparent or haze. Okay, so luminance transmittance is defined as the ratio of transmitted light to the incident light on the material. The value is generally reported in percentage of light transmittance. Like if you see, if you consider two polymeric materials over here, if you are having poly methyl methacrylate, which we can consider as a transparent material, and if you take second material as a polypropylene, can you see polypropylene? Polypropylene is having some haziness. It is not a transparent material, correct? So if you want to calculate the transparency of that material, you can calculate in the in sense of percentage, correct? So for example, transmit 90, if polymethyl methacrylate, if you consider, in that you can get the transmit, it can transmit 92% of the normal incident light. Okay, so whatever, if you are incident 100% of light, it will it will transmit 92% of light from it. Okay, so that in that way you can calculate the transparency of your polymeric material. Okay, and the very next property is nothing but the color. As you all of know about the color properties of polymeric materials. Okay, the the color precision process requires three things: a light source, an object, and an observer. Okay, at what kind of light we are inserting on your polymeric system, that will reflect your that kind of light to your observer, or you can say to our eyes. Okay, these are some instruments used to identify the color of your polymeric systems, or you can say color of the specimens. Okay, specular gloss is defined okay, is nothing but the measure of your gloss of your polymeric films or polymeric material. Okay, the specular gloss is defined as the relative luminous reflectance factor of a specimen at a specular direction. Okay, the gloss generally we calculated at different angles like 60 degree, 60 degree, 82 degree, 20 degree, in that way. Okay, at at various angles, how much gloss is present on your polymeric system, that can be calculated or that can be presented for measurement of gloss. Okay, the light beam is directed towards the specimen at a specified angle, as I have mentioned right now. Okay, and the light reflected by the specimen is collected and measured through the detector. Okay, and in that sense, the gloss we obtain. Okay, and we can calculate the gloss accordingly of your polymeric material. Okay, generally ASTM D2457 and D523 methods, standard methods, have been used for determination of your gloss of polymeric material. Okay, gloss is nothing but shining of your polymeric surface. Okay, okay, so for now, for the properties of polymer or testing of polymers, this much is from the this much from our side. Okay, is anyone having any doubt for testing of polymers from yesterday and today's lecture? Because here we are covering up of your polymer testing part. Okay, so I think all of your syllabus have been covered, only I think some part of rheological properties. Okay, rheological properties have been remaining from Jyoti sir. Okay, I think he will complete that rheological part on day after tomorrow's lecture, that is I think on Thursday's lecture. Okay, that will be your last lecture, I think, whichever the lecture will be there on Thursday. Okay, the Thursday lecture,
So
I think
last lecture related to what is?
see, whatever the plastic testing part or testing lectures. Okay, yesterday's and today's lecture is related to your plastic testing part. Okay, and I think Jyoti sir have will be continue with that rheological characteristics or rheological properties of polymer. I think that some part is remaining from his side. Okay, so tomorrow there is a lecture on environmental issues of polymers. Okay, that lecture will be conducted by me only. I will conduct that lecture. Okay, by your as per your syllabus, environmental issues is your last lecture, but that lecture I will conduct tomorrow. Okay, so accordingly, whatever the remaining part from Jyoti sir, he will conduct that part day after tomorrow, in day after tomorrow's lecture. Okay,
Okay.
now you understood the part. So we will see the environmental issues of polymeric substances, polymers, plastics, or whatever the type of polymers on environment. Okay, that we will see in tomorrow's lecture. Okay, yes. So we will stop here.